Alright, all. So we're going to move on to the final chapter of the course, which is chapter 13. And we're going to talk about coordinate geometry. And when we say coordinate geometry, what we mean is using the tools that we have from both algebra, so combining algebraic tools with geometric tools. And the combination of the two will help us solve even more problems, which is fantastic. So, the first thing I need to talk about, well, what do I mean by a coordinate? Well, a coordinate is an ordered set of numbers that labels where a point is in space. And by space, well, depending on how many dimensions you want to deal with, it can be the plane, so 2 dimensions, or it can be kind of 3-dimensional space, 3D space, etc. You can kind of imagine in math, maybe you'd want to talk about 4-dimensional or 5-dimensional space just by listing enough numbers that you could imagine something like that. For our purposes, we're just going to be talking about the plane. So we're going to be talking about the Cartesian plane. So we will limit our study to the Cartesian 2-dimensional plane. So, what I mean by that is that, well, if we think about what's going on here, we need an ordered set of numbers that labels where a point is in space. Now, I want to put a little asterisk here. Well, the label where something is in space, if you think about it, the best you can do is to say where it is compared to something else. So in terms of the location relative to some, what do I want to say, distinguished point. So relative to some chosen point. And that's kind of the crux of this, is all we can do is say how far a point is from some chosen point. So let me kind of show you what I mean. So we're going to choose a point here. This is going to be our chosen point, and we usually call the chosen point the origin. And the way we're going to decide where a point is in space in terms of coordinates, well, we're going to say how far is that point horizontally, how far is that point vertically from the origin. So we need some units, so let's mark off some units. So, for example, if I pick this point here, well, what coordinate could I give it? Well, we need 2 numbers, and the way these work, we're going to say how far it is in the horizontal direction, and the horizontal direction is usually denoted by x, and then how far is it in the vertical direction compared to our chosen point, the origin. And we denote the vertical direction by y. So, if we look here, this chosen point is 3 to the right, and we're thinking of the right as the positive direction. We can think of this as a number line. The right is the positive direction, the left is the negative direction. So this point is 3 units over to the right of our origin, and it is 1 unit up. So a label for this point would be something like 3, 1. Well, let's pick a different point. Let's say this point here. Well, that point, how far is it over in the horizontal x direction? Well, it is 1 unit to the left. So we'll say that this is -1 as its, or has -1 as its x coordinate. And where is it in terms of the vertical axis? Well, let me use the black again just to keep the colors consistent. Well, it is -2 down, or 2 down, so -2 on the y-axis. So we can give this coordinate point -2 in y. So hopefully you get a feel for what's happening here. Let's just do one more just to make sure we get it. What about, I don't know, this point here? So that point there, well, it is 4 over in the x direction, and it looks like 3 down. So it's -3 in the y direction. So this point has a coordinate of 4, -3. Oh, let's do, I'll tell you that the origin, well, it's 0 over from the origin, and it's 0 up and down from the origin. So the origin has coordinate 0, 0. And maybe one more point. Let's say this guy here. That guy there is directly above the origin, so it has an x coordinate of 0. It's on the same vertical line as the origin, but it's 3 up from the origin. So that point has a coordinate of 0, 3. So nothing huge there. That's just how coordinates work. I will make a quick note. This isn't the only coordinate system. So this one here, by the way, is called the Cartesian coordinate system, or rectangular. And it's named after the French mathematician René Descartes, back in the 1600s, who came up with this idea of coming up with a nice way of determining where points are in space compared to other points. But this isn't the only way you can do it. Let me give you another example. We won't focus on this too much. But we pick our chosen point, the origin. We always have to pick a chosen point and compare. But another way you could do it, so let's do this. Let's say we had the point here. So in Cartesian coordinates, this would have the coordinate 1, 1. But another way you could describe where this point is, if you wanted to get from the origin to this point, rather than saying go to the right 1 and then go up 1, what you could say is go at a certain angle. In fact, this angle here is 45 degrees. And how far do you go? Well, if you think about it, we have a right angle triangle here. This has length 1, this has length 1. By the Pythagorean theorem, you can work out that the length of the hypotenuse is square root 2. So in something called polar coordinates, don't worry about this too much, but another coordinate system, you could give the point, so instead of 1, 1 in the Cartesian, in polar coordinates, you could give it as the length, which we call r for the length, and the angle, which we call theta. So the length is square root 2, and the angle is 45 degrees. In the rectangular or Cartesian system, it's how far you travel in the horizontal or x direction, and then how far you travel in the vertical or y direction. So just note that there's more than one coordinate system out there. In fact, there's loads of others. Nothing is stopping us from picking lines that go through the origin that aren't at 90-degree angles. We could do that. It doesn't, for various problems, it doesn't make a lot of sense, but for certain ones, it does. But we won't get to that. That's beyond the scope of this course. If you are interested in these kind of coordinate systems and figuring out what coordinate system would be the best for different problems, look at taking a course called Linear Algebra. Now, what we really want to talk about are lines. If you think we're doing geometry stuff, lines are really important to us. So let's talk about lines. In some sense, there's three types of lines. So let's draw some examples and figure out how we can represent them algebraically. So remember, we're going to use this Cartesian coordinate system. We have the origin. And let's say we have a line. Let's put some units here. Let's say we have a line here. A nice horizontal line. Well, let's pick some points on this line. Here's a point. Well, that point is cutting through the y-axis, so the x-coordinate is 0. And the y-coordinate is, of course, 2. Well, let's look at another point on the line. How about this point? Well, here, the x-coordinate is -2. It's over 2 to the left of the origin. And it is still 2 above the origin in the vertical direction. So that has coordinate 2, 2. Well, let's look at one more point. This point, well, has x-coordinate 3 and y-coordinate, you guessed it, 2. So here's our horizontal line. If you had to say if you had to describe all points on this line, you would say something along the lines of, well, the x-coordinate can be anything, but the y-coordinate always equals 2. So the equation for this line is, well, y equals 2. X can be anything that you like. And there's nothing special about 2 here. We could draw our horizontal line wherever we want. So in general, for horizontal lines, have the equation y equals a for some number a. So they're horizontal lines. What about vertical lines? Well, let's draw a vertical line. How about this guy? So again, we know some points on this. This one's pretty easy. We know the y-coordinate is 0, and the x-coordinate is -3. It's 3 over to the left of the origin. Well, what are some other points on this line? Well, there's this point here. This is 3 over from the origin in the horizontal direction, and 3 down from the origin in the vertical direction. So its coordinate is -3, -3. And maybe say this point here, well, its coordinate, well, it's -3 in the x direction and 1 in the y direction. Or we can, there's nothing special about integer points. We could have a point here, maybe that guy there has x-coordinate -3, and y-coordinate, that looks like what, like -2.6 or something. Nothing special about integers. The points can be any real number that you like. But the point is, if you had to describe all points on this line, you would say, well, the y-coordinate can be anything, but the x-coordinate is always -3. So the equation for this line is y, or sorry, not y, x. It's x equals -3. And again, there's nothing special about the number -3. This will work for any number that you like. So for vertical lines, the equation is x equals a for whatever number a that you like. So that's how to draw, or that's how to come up with equations for vertical lines. And let's just do a quick example. Let's sketch the lines y equals -2 and x equals 1. Okay. Well, the line y equals -2, well, all points on that line have y coordinate -2, so it's going to be a horizontal line passing through -2 on the y-axis. So here is the line y equals -2. And the line x equals 1, well, all the x coordinates are the same, so it's going to have x coordinate -1, and the y's can be whatever. So here's a sketch of the vertical line x equals 1. So now that we have those, horizontal lines and vertical lines are easy. So we are going to talk about lines that aren't vertical or horizontal next. For diagonal lines at any angle, we'll have to come up with another way of writing them. So let's see if we can figure out a good way of coming up with an equation. So let me pick, you only need 2 points to make a line, of course, so let me just pick 2 points. So let's say the points are this point here, so this is 0, 1, and let's have another point. I don't know, let's pick this guy. Let's pick, so this is the point 2, 2. So our line looks something like that. So let's see if we can come up with a way of writing an equation for this line. Well, we want that if we give an x value, there's a y value to go with it. So what we're looking for is we're looking for something of the form this. So y is some sort of function of x. So let's see if we can kind of figure out what's happening qualitatively and then try and translate it into an expression mathematically. So let's pick another point on our line here. Maybe let's pick the point here. And I'll tell you guys that this point is 1 3/2. Well, what does it look like that's happening? Well, it looks like, and it's good to say for every something you do, something else happens. So the way we're going to phrase it is, for every 1 we move over to the right in the horizontal direction, what happens in the vertical direction? It looks like here, in fact, let me zoom in. I'm just going to zoom in here. So I'll draw a little box just to give myself a little more room. Oh, hold on, maybe I'll do this. I'm going to try a new feature here. I'm going to try this to zoom in. So let me do that. I'm going to drag this, and I should be able to zoom in. Oh yeah. Let's see how this works. Okay. So it looks like for every 1 unit I move over in the x direction, so every 1 unit to the right, it looks like I move up a half unit in the y direction. So this is 3/2. So it looks like here we have a 1, and here we have a 1/2 as the size of our triangle. And if you think about it, by similar triangles, any point on this line that you pick, let's say we'll pick a point all the way up here, and I make a triangle like this, well, these vertical lines, of course, are parallel. So the little green triangle here and the big red triangle are going to be similar, which tells us that the sides are going to be in proportion to each other, which is really, really cool. So that tells us for every, no matter what point we move over, for every, let's say, x we move over in the x direction, x is the horizontal direction, we move up half, that's not a good 2, half of that amount in the y direction, or vertically. So that's kind of our first note. So it looks like that we're moving up, in this example, half as much as we move over. But the other thing that we have to note is we're not starting at the origin. We're starting 1 above the origin. So since we're not starting at the origin, we're starting 1 above. Well, we're just going to have to add 1 to this in order to make our line work. So here's our equation here. Y equals a half x plus 1. That amount we talked about for every x we move over, we move up a half x. This is called the slope of the line. That doesn't look very good. Let me rewrite that. That tells you the steepness of your line. And this here, this is the Y-intercept. This is where your line cuts the y-axis. And you can see here our line cuts the y-axis at 1 on in the y direction. So the y-intercept is 1. So in general, let's see if we can figure this out. So now that we have the equation of our line, y equals a half x plus 1, let me kind of sketch that just once again. So we had the point 0, 0. Here's the point 0, 1 on our line. And we also had the point 2, 2. So let me draw this line again. There's our line there. So we can ask, well, how do we find points on the line? Well, it's pretty easy. In fact, all we're going to do is pick an x value and solve for the related y value. Okay, so what about when x equals 4? Well, when x equals 4, then y is a half times 4 plus 1. So that's 2 plus 1, so that's 3. So we know the point for 3 is on our line. Well, what about something like when x is, I don't know, negative a third? What does that look like? Then y is a half times negative a third plus 1. So a half times negative a third is negative a sixth. 1 times negative 1 is negative 1. 2 times 3 is 6. And I'm going to change 1 to 6 sixths. So this becomes 5 over 6. So we have the point when x is negative a third, y is 5 sixths. So let's see if we can draw that. So negative a third is somewhere around here. So here is the point, negative a third and 5 sixths. And you can see it jives with our diagram as well. It looks like on the y-axis we've gone up about, maybe I'll use a different color there. Let's use red. It looks like we've gone up about 5 sixths. And our y value is, or sorry, our x value is around negative a third. So it jives with the diagram. That point is on the line. Well, here's another question I can ask. Is the point negative 1, negative 3 on the line? Well, we have an x and a y value. Let's plug them into our equation and see if we get equality. So, does negative 3, which is our y value, does that equal a half times negative 1 plus 1? Let's check. Negative 3. Well, a half times negative 1 is negative a half plus 1. So negative 3 doesn't equal 1 plus negative a half is a half. So they don't equal, so the answer is no. So the point, we can see negative 1, negative 3. Where does that lie? Well, negative 1 is here. Negative 3 is somewhere down here. So it's not even close to our line. But you can check algebraically just by plugging in your x and y value. Because remember, any point on the line makes the equation true when you plug in its x and its y value. So we'll talk a little bit more about slope and y-intercept, and we'll do a couple of problems. And then we'll talk about parallel lines and perpendicular lines. Well, if you remember with slope, let me kind of draw this again. I'll just draw some sort of line here. Doesn't really matter what it is right now. So there's our line. And remember, we can think of this, we can move over 1. Maybe I'll make it a little bit larger. We can move over 1 in the vertical or in the horizontal direction, and then figure out how much we're moving over in the vertical direction. And what's cool, like I said before, is that any point on this line, you're going to get a similar triangle idea. These lines here are parallel, so we get a similar triangle, just like we talked about in section 12.3. So whatever this is, let's call this A. So I'm going to call this, let's call this Y. This value here. No, let's not call it Y. Let's call it M. I like the letter M, and you'll see why in a second. So, what does that tell us? So, it tells us this will be A, this will be B. It tells us that the sides, the corresponding sides, have a common ratio. So it tells us that, well, the big triangle, let's say, let's do it like this. So, oh, that's erasing. I don't want to erase. I want to highlight. So B over M is going to have the same ratio as A over 1. So let's write that down. So B over M, that's our vertical sides. Our big vertical side over our small vertical side is going to have the same ratio as A, our big horizontal side, over our small horizontal side, 1. Which is pretty cool. And so, if we think about this, we want to kind of have this in terms of, let's call this, oh, no, let's solve for M. That's what I want to do. So, let's solve for M here. So, I'm going to cross multiply. And what do I get? I get that 1 times B is B, and A times M is A times M. Going to divide both sides by A, and I get that B over A equals M. So what does that tell us? That tells us that kind of how much we move in the vertical direction. You can always figure that out by saying how much you move for any point, the difference between the x coordinates of your 2 points and the difference between your y coordinates of your 2 points. If this point here had coordinate, let's say, x1, x2, and this point here on your line, sorry, not x1, x2, that makes no sense, x1, y1, and this point was x2, y2, then you could figure out this m, this slope. Well, this is a vertical line. Or sorry, this is a vertical line. Let me highlight that. So the length of this line is just the difference in the y coordinates. So the length of B here is just going to be, sorry, not B, y2 minus y1. So that length there is y2 minus y1. It's the difference in the y coordinates. And this point here, this kind of corner point, well, this is the point x2, y1. So that might help you see it a little bit better. Because it's on the same horizontal line as x1, y1, so it's going to have the same y coordinate. And it's on the same vertical line as x2, y2, so it's going to have the same x coordinate. So you can see that the length of this line, well, it's the difference between the y values. If this was 7, if y2 was 7, and if y1 was, say, 2, then the length of this line is going to be 7 minus 2, which is 5. And similarly, for the x coordinates, well, the length of this line is going to be x2 minus x1. So let's write that in. So here we are. What does this tell us? This tells us that we can figure out the slope just by looking at the coordinates of any 2 points on the line. So another way of thinking about it, if you like, you might see it written as delta y over delta x, and that little triangle there means delta, or change in, which is how much y changes from one point to another over how much x changes from one point to another. And the other way you might see it is you might see it as rise over run. That's another way. So that's not too bad. So that's all m is. Using the idea of similar triangles, you can calculate it just by your change in your y values divided by your change in your x values. So let's do a couple of examples, and let's see if we can use this both to determine equations of lines given some points, or maybe we could do something along the lines of we can guesstimate slopes. So let's do a couple of examples. So the first example is going to be find the equation of the line passing through. I'm just going to pick 2 points, -1, 4, and 3, let's do 3, -2. Now, whenever I do these problems, whenever I have coordinate geometry problems, I like to sketch everything that I know. So I'm going to do that. So I know it's going to pass through the points -1, 4. So -1, 4 is here. And 3, -2 is here. So I know my line is going to look something like that. Remember, lines go infinitely far in either direction. So what can I glean from this? Well, I can glean the following things. So the first thing that I glean is that if I move 1 unit to the right in the x direction, it looks like I move down in the y direction, and probably by, I don't know, maybe like between 1 and 2 units. So what I can glean from that, so my estimate doesn't have to be awesome, but I can glean that my slope, m, is going to be negative, and probably around, say, -1 to -2. So somewhere around those that value. The other thing I can glean from my diagram is it looks like the y-intercept is around 2. It might not be exactly 2, but it's around 2. So my y-intercept is going to be somewhere around 2. And obviously my sketch isn't particularly awesome, but that's okay. Just sketching these things, you can just get a feel for what your answer should look like. Okay, so now we have to solve for this equation of a line that contains these 2 points. All right, so the first thing is our equation is of the form y equals mx, where m is our slope, plus b. Remember, b is our y-intercept. That's where our line cuts the y-axis. But we can solve for our slope, so let's do it. So remember, m is always the difference in our y-coordinates over the difference in our x coordinates. The only thing is we need to be careful. We can pick either point to be y1 or x1, y1, but we just have to be consistent. So let me pick the second point, not for any particular reason. I'm going to call this one x1, y1. That'll be our first point. And our second point, this guy will be x2, y2. We'll end up with the same number, the same slope, no matter which way we do it. So let's fill this in. So y2 is 4 minus y1 is, negative 2. Okay. And we're going to divide by, well, x2 is negative 1, and we're going to subtract x1, which is 3. So we simplify this. 4 minus a minus 2 is 4 plus 2, which is 6. And minus 1 minus 3 is minus 4. So we have a positive divided by a negative, so our answer is going to be negative. And we can simplify this fraction. 6 divided by 4 has a common factor of 2. 6 divided by 2 is 3. 4 divided by 2 is 2. So this has a slope of negative 3/2. Great. Okay, so we know our slope. So m is negative 3/2. I'll put a box around that just to know to look there, so it's pretty clear. Great. So now we have the equation. We can fill that in. Y equals negative 3/2 x plus b. So another way to look at this, rather than saying for every 1 unit we go over in the x direction, we go down 3/2 of a unit, I can also read this by saying for every 2 units, I go to the right, I go down 3 units. So that's another way of reading it. It's the same thing. Rather than having a 2 here, you could have your 1, and then your 3 would be 3/2. Same thing. Similar triangles means that it's the same thing. All those ratios are in proportion, so, or are equal, in fact. All those ratios are equal, so you're good to go. All right, so we have this equation y equals 3/2 x, negative 3/2 x plus b. We just need to find b. But we can just plug in any point on our line. So let's go ahead and do it. Why not? So let's plug in, I don't know, maybe I'll scroll back up and we'll pick one. It doesn't matter which one you plug in. Let's plug in 3, negative 2. Let's plug in this guy. You can check. You're going to get the same answer if you plug in negative 1, 4. But I'm going to plug in 3, negative 2. Okay, so let's scroll down. So the y value was negative 2. So that equals negative 3/2 times, it's positive 3, wasn't it? 3 plus b. Okay. So let's solve this. So we get that negative 2 equals negative 3/2 times 3 is negative 9/2. You can, if you like, you can think of 3 as 3 over 1 and then multiply fractions. Plus b. We'll add 9/2 to both sides. So we get negative, I'm going to change negative 2 to negative 4/2 just to get a common denominator, plus 9/2 equals b. So just here we're adding 9/2 to both sides. And the negative 2 I just made into the equivalent fraction, negative 4/2. So this becomes 9/2 minus 4/2 is, of course, 5/2. So that's our b. So our final equation, let me actually put a box around that because that's the other important bit. So our equation is as follows. It is y equals negative 3/2 x plus 5/2. And you can see that that kind of jives with our guess. If we go back up and look at our estimate, we said that, well, the slope was going to be negative and probably around -1 to -2. And negative 3/2 is like negative 1.5. Perfect, that makes sense. And our y-intercept looked like it was around 2. In fact, it was just above 2, 2.5. We're happy with that. So our estimate is a good way of just checking that it makes sense. So our answer does make sense with the diagram that we'd draw. So let's do another problem before we move on to perpendicular and parallel lines. So let's find the intersection point of the following two lines. Let's do y equals 2x minus 1 and y equals -1/3 x plus 4. Okay. So again, before I even start anything, I like to sketch this. So let's make a sketch of both lines. Remember, to find points on the line, just plug in some x values. The easiest x values to plug in are 0 and 1. So we'll call this star. We'll call this double star. So let's look at star. When x is 0, well, y is 2 times 0 minus 1. Obviously, that's going to be the y-intercept. So our point is 0 minus 1. And when x is 1, well, y is going to be 2 times 1 minus 1. 2 minus 1 is 1. So we have the point 1, 1. So let's graph these. So we have the point 0, minus 1. Let me put in some units here. Again, this is just a sketch. You don't have to be super accurate. Oh, we need to go up to 4, actually, so let's do that. Okay. So here's the point 0, minus 1, and we need the point 1, 1. Here's the point 1, 1. So our first line, which I'll do, I guess, in red, will look roughly like that. For the second line, double star, well, let's do the same thing. Let's pick some x values, calculate the y value, and then say what the point is. So again, we can use whatever values we want. 0 and 1 are always good choices. 0 you can always read off. That's just going to be the x-intercept, or sorry, the y-intercept. Remember, the y-intercept is where the line cuts the y-axis. So it's going to be when x equals 0, y equals 4. So that one is easy. We have the point 0, 4. And we also have the point, actually, I don't particularly like this sketch. Let me just change it a little bit. Just to make the tick marks more spaced out evenly. That looks a little better. So here we have the point 0, 4. And we could plug in 1, but maybe I won't. And I'll tell you why I won't. You would be fine to plug in 1. You would get another point. But I'm looking at here. I know we have a denominator of 3 in our slope. I don't want to end up with a fraction. So if I put in something that has a multiple of 3, then that will cancel out. So I'm going to do that. In fact, I'm going to put in 3. So let me erase the 1. And let me put in a 3. Nothing wrong with 1. Just saves a little bit of work. So this is going to be -1/3 times 3 plus 4. So negative a third times 3 is negative 1. And then negative 1 plus 4 is 3. So we have the point 3, 3. And up here, I guess I should write we have the point 0, 4. So we have the point 3, 3. Let's sketch that. That is here. So, the intersection of these two lines, well, it looks like it's kind of between where, in the blue line, in the second line, where y equals 4 and y equals 3. So it looks like the y value is going to be 3 in the bit. 3 point something. Good. And it looks like the x value, well, if we draw a line down here, it looks like the x value might be 2 and a bit. So that's kind of our estimate. All right. So let's go ahead and solve this problem now. So we want to find the intersection point. Now we think about that. We want to find a point that causes equality to happen in both lines. So we want to find a point, or I should say the point, not a point, the point that satisfies both equations. So at that point, the equations equal. So at that point, we have that single star actually equals double star. Because this point here, this intersection point, maybe I'll do it in green actually because it's kind of special. That satisfies both equations. So at that point, both equations equal. So we can set them equal to each other. And look at this. So both of these equations equal y, so they equal each other. So since y equals 2x minus 1 and y equals negative a third x plus 4, for that same y value, we got to figure out what it is, but it's the same, they're going to equal each other. So let's do it. So 2x minus 1 equals negative a third x plus 4. And again, let's make our lives a little easy. I'm going to get rid of these fractions. I'm going to multiply everything on both sides by 3. You don't have to do this, but when I have fractions in my equation, that's something I like to do. Just get rid of my denominators. So this becomes 2x times 3 is 6x. 3 times negative 1 is minus 3. So that equals 3 times negative a third is negative 1. So we have negative x. And 4 times 3 is 12. So what do we have here? We have that. Well, 6x minus 3 equals negative x plus 12. Let's add x to both sides, and let's add 3 to both sides. Okay, so what do we get? Well, 6x plus x is 7x. Negative 3 plus 3 is 0. Negative x plus x is 0. And 12 plus 3 is 15. Divide both sides by 7. And we get that x is 15 sevenths. Which jives with our guess. Remember, we said that x was going to be 2 and a bit. And if we convert this to a mixed number, or you could do long division, this is 2 and a seventh. So that jives with our guess. That makes sense with the diagram that we drew to estimate. Excellent. Okay, so now that we know x, we can just solve for y. So let's plug x into either equation. Okay. So let's plug it into, I guess, the first one. That's a little easier. So we have y equals 2 times 15/7 minus 1. So what is this? So y is 30/7 minus 1. I'm going to change 1 to 7/7. And 30/7 minus 7/7 is 23/7. And if you convert this to a mixed number, just to see where it is on the number line, this is 3 2/7, which jives with our guess of 3 and a bit. So this is excellent. Our answers seem to make sense with the diagram that we drew. So the intersection point is 15/7, and the y value was 23/7. Or you could write it in terms of a mixed number. Doesn't matter. So there we go. We found where those two lines intersect.